Hello children, it's a great day and happy to have you all back once again. So today in physics class, we are going to discuss equipotential surface, electrostatic potential energy for the collection of point charges and electrostatic potential energy for the dipole in uniform electric field. So these are the topics for today. I want to start this session with a small conversation between two people. The first one is asking, why do we use U, capital U, as a symbol for potential energy? Is there a hidden meaning behind the capital U, like Ke for kinetic energy? The second person is answering, because you have a lot of potential. So meaningful, no? Yes, you have a lot of potential. Bring it out, use it well. Shine like a star and don't let anyone ever dull your sparkle. Okay, children? So let us start today's session with this positive thought. So in last session, yesterday, we have discussed about electrostatic potential due to point charge, electrostatic potential due to electric dipole. I think you may remember. Today in this session, we are going to discuss equipotential surface, electrostatic potential energy for the collection of point charges and electrostatic potential energy for the dipole in uniform electric field. These are the topics for today. Let us start it with equipotential surface. So what do you mean by equipotential surface? An equipotential surface is a surface on which all the points are at the same potential. So if you consider a surface, and in that surface if all the points are of same potential, that will be called as equipotential surface. You yourself know that the meaning of the word EQUI is nothing but same, right? Yes. So here that is what is the definition for it. So we are going to see two examples to understand it better. So look at the first example, equipotential surface in the case of point charges. Okay, now let us consider the charge of magnitude capital Q is placed at the center as given in the diagram over here. So look at the first circle, that is green color circle given over here. So you know that it is a green color in all the points present in this green color circle. We know that it is at the same distance from the center, isn't it or not? So you know the formula for electric potential also for the case of point charges, 1 by 4 pi epsilon naught Q by R. Okay, so 1 by 4 pi epsilon naught Q by R. So here in this case, automatically what happens is, for all the points present in the first circle, it will be having the same potential, because after all they are at the same distance from the charge Q. So automatically all those points present in the first circle will be having same potential. So we can call it to be a equipotential surface. Now look at the second circle. So in that case also all the points on the present in the second circle will be at the same distance from the center. So they also will be at the same potential. So you can call the second circle, the points in the second circle, to be of same potential. So the circle itself can be called as the equipotential surface. But we will not be calling a circle to be a surface here. So what we can do is we can imagine it in a three-dimensional now. So automatically the circles are becoming spheres. Yes. So here for a point charge, the equipotential surface are nothing but concentric spherical surfaces. But what do you mean by the word concentric? Concentric is nothing but, here concentric spherical surfaces are nothing but the spheres of different radius but of same center. So in that center the charge is present. Do you understand, children? So that is about the first example. Now pass on to the second one, that is equipotential surface of a uniform electric field. So look at the electric field given over here in the diagram. You can see that it is pointed towards the right. So in the left side, that means that in the left side the positive charges must be present, or maybe in the right side the positive negative charges must be present. Okay, look at here in that case they have given that the equipotential surfaces are set of parallel planes. But how? So look at the first plane over here. So for all the points present over there in the plane, we can see that they will be at the same distance from the charges present in the left side, isn't it or not? Or maybe if you consider the charges are present in the right side, there also it is going to be of same distance. So automatically for all the points present in the first plane, they will be of equal potential. So we can call that to be a equal potential surface here. The same thing is true for the second and third parallel planes too. But remember, the potential will be different when you are speaking about the first plane and the second plane. The same thing over here. So even though we are calling the spheres to be of same potential. That is true only with that particular sphere. If you are moving from one sphere to another sphere, the potential always changes. So what happens in this case, when comparing to the first sphere, the second sphere will be having less potential, the third one will be having less potential, because here we can see we are speaking of the positive charge, plus q charge at the center. Okay, now think over what will be the equipotential surface in the case of a dipole. So take it as your homework, think over and tell me. Now we are going to pass on to the properties of equipotential surface. So we are going to discuss two properties. Let us discuss about it one by one. Look at the first one. Work done to move a charge between the 2 points in an equipotential surface is always 0. So when you have to move charge of any magnitude, any charge of any magnitude, okay, between 2 points in the equipotential surface, that is always equal to 0. How come? So look at the diagram given here. Q is the charge present in the center. So imagine that we are bringing another q charge from the point B to A or A to B, whatever it is. They are equipotential surfaces after all. So in that case, the work done is given by the formula Q into VB minus VA, isn't it or not? But we know that VA is equal to VB for equipotential surface. So automatically whatever is given in the bracket is going to be 0. When it is multiplied with the Q, it is again a big 0. Okay, so the work done is 0. So whatever may be the magnitude of charge, 1 coulomb or 2 coulomb or million tons of a coulomb, whatever it is, here we can see that if you are moving a charge from one point to another point in an equipotential surface, it is going to be, the work done is going to be 0. That is your first property. Second property, electric field is always normal to the equipotential surface. You could have seen it in this diagram even. So always this electric field is perpendicular to the equipotential surface. But how come? That is what we are going to explain now. So please make a note of this particular diagram. It is not given in your book. So here you can see that always the electric field is perpendicular. If not, what happens? So if not, the electric field is making some angle with the horizontal, right? So here you can see that the capital E is making some angle with the horizontal. So it is making an angle theta. So the horizontal component can be taken as a parallel component, that is, it is equal to E cos theta. Similarly, the perpendicular component will be E sin theta. So anyway, E sin theta will become 0 as it is acting perpendicular to the force. That is, in that case, E sin 90 degree, right? So automatically, in that case, automatically it is acting perpendicular to the equipotential surface. No work will be done because of it. But because of this horizontal component, that is tangential component, E2 parallel component, automatically what happens is the charge may tend to move in that magnetic field. That is, in that case, the work done is not equal to 0 as this value is not equal to 0. Do you understand? So you will understand it even more better when you are going through this particular derivation. So this derivation is also not there in your book. Please make a note of it. So we know dV is equal to minus E dr, isn't it or not? Isn't it? Yes. Now in that case, if dV is equal to 0, what happens? Because equipotential surfaces, potential difference between 2 points is 0. So dV, the change in the potential, is going to be 0. So automatically E vector dot dr vector is going to be 0 again. So in that case, E dot dr is E vector dot dr vector is 0. So it is in the dot product formula. So what is the formula for A dot B? So A vector dot B vector can be written as modulus of A modulus of B cos theta, right? So it is E dr cos theta now. So E cannot be 0, dr cannot be 0, cos theta must be 0. That means that the theta must be equal to 90 degree always. So here we can see that the angle between E and dr must be equal to 90 degree all the time. Okay children, so that is all about the equipotential surface. Now let us pass on to the next one. So equipotential surface we can expect in 2 marks or 3 marks, and this particular question is a very important 3-mark question. Relation between electric field and electric potential. So again, please make a note. In your book, many steps are given over here in the here are skipped. Okay, they have missed many steps. So please, while you are after the class, please note down all the steps whatever is missed in the book. Okay. Now what I am going to consider here is, I am going to consider a charge Q. So it is going to be placed in the space, and now we are going to bring another charge, a unit positive charge plus 1. So we are going to try to bring that charge near to this positive Q charge. So whether we have to do some work or it will happen by itself. Yes, we have to do some work here. So what will be that work is equal to, as usual, dw is minus f dot dx, f into dx. So what is this minus stands for? So we are doing the work against the field, and that is why there is a minus sign. Okay children, now we know that E is equal to F by Q. Now replace, that is Q is equal to 1 coulomb, we know that because we are speaking about unit positive charge here. So Q is equal to 1 coulomb. So automatically you can replace F with E. So dW is equal to minus E dx. But what is dW? We know that dW is nothing but dV into Q. Okay, dW is equal to dV into Q. So here in this case we can write dW is as dV itself. dW is equal to dV, right? Because Q is equal to 1 coulomb. So what it makes, dV is equal to minus E dx now. Why it is minus E dx? Because in the previous equation we are replacing dW with dV now. So dV is equal to minus E dx now. So E is equal to minus dV by dx. So V stands for potential. So dV by dx is, dV is change of potential. What is dV by dx then? See, when it is with respect to time, we used to call it as rate of change of this one, right? But here it is with respect to distance now. With respect to time it is rate. With respect to distance it is called gradient, G-R-A-D-I-E-N-T. I think you might have studied about the same in your 11th standard in velocity gradient in coefficient of viscosity concept, right? Same thing here. So here this electric field can be called as the negative gradient of potential. Okay children, so this also explains why the electric field is having another unit. Normal unit for electric field is Newton per coulomb, but it has another unit also, volt per meter, which is actually derived from this particular formula. Okay, so we can represent this potential in 3 different dimensions as it is given in the next equation. Okay, so to understand this better we can discuss a example problem now. The following figure represents the electric potential as a function of x coordinate. Plot the corresponding electric field as a function of x. So they have given the diagram. From this you have to find out what is the corresponding electric field and you have to plot a graph with that. Okay, so have a close look at the diagram. So from 0 to 1 the potential is increased to 25. From 1 to 4 it is maintained as a constant. Then from 4 to 5 it is decreased to 0. So in this problem it is the variation is taken with respect to x. So we are taking the y and z components to be 0. We are considering only the x component here. So E vector is minus dV by dx I cap now. Okay, now look at the from 0 to 1 the slope is constant, that is dV by dx is 25 actually. So if dV by dx is 25, what is E then? It is minus dV by dx. So it should be minus 25 volt per centimeter I cap. Okay children. Now from 1 to 4 the that is dV by dx value is actually maintained as a, that is potential is maintained as a constant. So dV by dx should be equal to 0. The rate of, that is the change of the potential is 0, dV by dx is 0. So automatically E is also equal to 0. Now what happens from 4 to 5? The value is actually reduced. So dV by dx is equal to minus 25 volt per centimeter. So we know that this particular E is equal to minus of dV by dx. So minus of minus 25 is plus 25 volt per centimeter I cap. Okay, now we have to plot this electric field with respect to the coordinate, that is x axis. So how can we do it? From 0 to 1 the value is increasing from minus 25 to 0, then from 1 to 4 it is maintained as a constant, then it is increased to plus 25. So that is what is denoted by a red line in the graph here. Okay children, so we have discussed the 2 mark questions and we have discussed the 3 mark questions also. Now let us enter to the 5 mark question. Electric potential energy for collection of point charges. So I want you to recall what you have learned as the formula for electric field, electric force, electric potential. Right? Electric force is given by Coulomb's law 1 by 4 pi epsilon Q1 Q2 by R square, and electric field is given by the formula 1 by 4 pi epsilon naught. Yes, Q1 Q2 by R square. No, it is 1 by 4 pi epsilon naught Q by R square. Yes. Then what about potential? Then it is given by the formula 1 by 4 pi epsilon naught Q by R. Now we have to derive an expression for a potential energy generally, and then we are going to find it out for the collection of point charges. That is like your superposition principle. Okay. So now consider a charge Q1 placed at the space, and we are bringing another charge Q2 into the space. So there, in order to do that, we have to do the work against that field, right? So automatically the work is given by the formula Q2 into V. But what is V? V is because of the potential because of the first charge, that is 1 by 4 pi epsilon r Q1 by R. Substitute here, then the work done is equal to Q2 into V, and that is what is called as the potential energy. So whatever work is done will be stored as a potential energy. So capital U is equal to Q2 into V. So that is Q2 into V. So it is 1 by 4 pi epsilon r Q1 Q2 by R. This is the general formula. So in order to find out the potential energy in any case, what we have to do is whatever charge you are bringing, that must be multiplied with the potential because of the previous charges present over there. Okay, this is the thing. So now we are going to do it as a special case. We are going to derive, look into the charge configuration given in the diagram. At the point A we have Q1 charge, at the point B we have Q2, at the point Q3 C we have Q3. So in order to do that, in order to bring the charges to this point, we must have done some work, right? And that will be stored as a potential energy. So in order to bring these charges here, we can do it in two different ways. First, we can bring the one charges at one time, right? That is, all the charges can be brought together also, and all the charges can be, we can bring one charge, we can bring Q1 to the scene first, then Q2, then Q3, like that. So we are going to follow this second method, that is, we are going to bring one charge at a time, and we are going to find out what is the potential energy, then we are going to find out the addition of, that is, sum of all these potential energies. Okay children, so first of all, to bring Q1 to the scene, there is no need for it to do any work because there is no any other charge in the vicinity for now. So now we got to bring the Q2 charge to the point B. So we have to bring it to the distance R12. So now tell me from previous discussion what you can see in the board over here. It is Q2 into V, right? So here the same thing, Q2 into not V here actually, we can take it as VA, okay, because this is because of the first charge at the point A. So it is 1 by 4 pi epsilon r Q1 into R12. This is the potential because of the first charge which is present at the point A. So it is VA is equal to 1 by 4 pi epsilon r Q1 by R12. Now what is UB? UB is nothing but the work done to bring the charge to Q2 charge to the point B. So we are bringing Q2 charge, so it should be Q2 into VA because the Q1 charge is already in the picture now. So multiply this one, both 1 by 4 pi epsilon into Q1 Q2 by R12 will be the UB value now. So two charges are there now, we are bringing in the third charge. So that will be UC and it is U1A plus U1B because in this case to bring the charge Q3, we have to do the work against Q1 and against Q2 also. Okay, so now UC is equal to U1A plus U1B. What is U1A first? See, in both cases U1A and U1B, we are bringing Q3 charge, so write Q3 first, multiplied by, here it is against the first charge, that is Q1, so it is V1. So second case it is Q3 into V2. So what is V1? It is 1 by 4 pi epsilon Q1 by R13, or it can take it as R31 even. What is V2 now? It is 1 by 4 pi epsilon r Q2 by R23. So this is U1A and U1B. So to find out UC, you have to add them both. Add them both, you will get it as 1 by 4 pi epsilon r Q1 Q3 by R13 plus Q2 Q3 by R23. So this is your UC. So we got UB already. So this UB and UC has to be added up to get the final expression for the total potential energy stored because of assembling all these charges in the vertices of this triangle. Do you understand children? So this is about the general formula for it. So this is just like your superposition principle again. Okay. Now let us discuss an example to understand it even more better. Four charges are arranged at the corners of the square. First triangle, now square. PQRS of side A as shown in the figure. Find the work required to assemble these charges in the given configuration. Suppose a charge Q dash is brought to the center of the square by keeping the four charges fixed at the corners. How much extra work is required for this? So actually speaking, we are bringing 5 charge, but the second case we can discuss it later. First we will discuss about the first subdivision. See, look into this square given over here, PQRS, right? Let us start it from P. First, in order to place the plus Q charge at the point P, there is no need for us to do any work. So the first subdivision is WP is 0. Now what is WQ? Work done to bring the charge minus Q to the point Q. In order to do that, you should take the charge and multiply it with the potential because of the previous charge. We know it, we know the rule, right? So minus Q, we are bringing minus Q charge here. So minus Q, WQ is nothing but minus Q into potential because of the previous charge. What is the previous charge in the scene already? it is plus q. It is at the distance of a. So we can write the formula as 1 by 4 pi epsilon naught q by a. So totally it is minus q square by 4 pi epsilon naught a. Now two charges are there in the picture. We are bringing the third charge into the scene. So in that case, what is WR? WR can be written as the sum of two terms. Why two terms? Because we have two charges there already. See, with respect to the minus q charge present in the point q, it is very simple. We will follow the similar rule what we have done already. So plus q into this minus q divided by 4 pi epsilon naught a, the same thing. But what about the distance between p and r now? So that is what we have to note it down. So what is the distance between p and r? Just to join p and r. So look into the triangle which you are getting over there as PQR. So PR square is PQ square plus QR square, right? That is equal to a square plus a square, that is 2a square. That is nothing but root 2a, right? So the distance between p and r is root 2a now. That is why here they have written the equation as q into 1 by 4 pi epsilon naught. Why q? Because we are bringing plus q charge to the point r, not minus q charge. So q into 4 pi epsilon naught into minus q by a. Why minus q by a? Because minus q at the point q. So minus q by a plus q by root 2a. Okay children, now we can take the q out, that makes it to be q square. So that is here WR. Now WS. So now three charges are there at the picture. See, because of this charge at the point P and the charge at the point R, again you are going to take it in the same way, that is minus q multiplied by 1 by 4 pi epsilon naught into q by a. But because of this minus q present in the q, it is minus q by root 2a. So we are taking it out as a q, taking q out, it becomes q square. So in your book it is given as WS, please, WS is given as minus 1 by 4 pi epsilon naught q by a. Please make the change, it is not q by a, it is q square by a. Do you understand children? So in order to find out the total work done, it's enough if you are adding them all. If it is given in the question, we have to add them all to find out the total work done. Okay, now let us move on to the second subdivision. Suppose the charge q dash is brought to the center of the sphere by keeping all the four charges fixed. How much will be the extra work done in this case? See, remember here in this case we have plus q charges and 2 plus q charges and 2 minus q charges. So at the center, when you have to bring it to the center, the center point is at the same distance from all the four charges, right? All four corners, right? So in that case, the potential produced because of two positive charges will be cancelled by the potential because of the two negative charges. So there is no need for it to do any extra work to bring any extra charge to the point. If you are bringing it near to this charge configuration, automatically that will move to the center without doing any extra work at all. Interesting, na? Okay. So meanwhile, it is a meme time. Okay, time out, your favorite time. So now we can have some fun by looking into few memes over here. Okay children, the first one, please conserve energy, turn off the lights. That is a notice that was stuck over there. So look into the reply for it. Jokes on you, energy is always conserved. Yes, after all, energy is always conserved. But please remember, we have to conserve the energy by turning off the switches, no other go. Okay, look into the second one. My favorite kind of energy is potential energy. Why? Think over. Look into the third one. Potential energy converts to kinetic energy in 3, 2, 1, 0 seconds, right? It is getting ready to jump over to the person that over there. Okay, next one. If I was flying, I have kinetic energy, and now that I am sitting, I have potential energy. So the words may think in this way, right? And there is something interesting, some interesting thing is there inside this meme. So try to find it out, figure it out. Okay, the next one. When you just finished learning about kinetic energy, just to learn there are a lot more forms of energy. I think this people's favorite pet animal must be cat, meme creators favorite pet animal. Okay, look into the last memes. When you still don't understand what kinetic energy and potential energy is, but this meme is not for us. We are very well we are thorough with all this potential energy and kinetic energy concepts after all, right? Okay, look into the last meme for today. When the gravitational potential energy hits you hard, when you are moving in the roller coaster, you can feel this thing. Look at the expression of that boy over there. Okay, so in the gravitational potential energy hits you hard. So that's all for today, and you can see, you can create memes of your own choice, right? Okay children, so next, the last topic for today, the electrostatic potential energy of a dipole in a uniform electric field. See, maybe sir would have explained about you this, the torque experienced by a dipole in a uniform electric field. These two questions are important 3-mark questions. Okay, so what happens when you are placing an electric dipole in a uniform electric field? Automatically it will experience a torque, and that will tend to rotate it, right? So it will try to align it in the direction of the electric field. You must have studied about it, right? So now in this case, so in order to move it against that, because always it will tend to, that torque will tend to rotate it and align it parallel to the field. So we are doing some work against this, or we are applying some torque against this torque created over there to move it to some position. So in that case, whatever work is done by us, that will be stored as the electrostatic potential energy. So that is what we are going to discuss now. So look at the dipole given over there, A, B. So A and B represents 2 points where minus q and plus q charges are kept, and they are at a distance of 2a as usual, and they are making an angle of theta with that of the electric field over there. So what is the work done formula here? So suppose if you have to move it from the position theta dash to the position theta, what will be the formula then? Normally work done is force into displacement. Here we are speaking about turning effect of it. So it is torque external, tau external into d theta. Since tau external is equal and opposite to tau E, see, tau external is whatever force we are, that is whatever torque we are applying, and tau E is the natural torque that is created over there while we are placing the dipole in the electric field. So it is given by the formula P vector cross E vector, that is Pe sin theta. That is what you have derived already. So substitute it over here in the equation 1.49. So that is work is equal to theta dash to theta Pe sin theta d theta. Take Pe outside. On integration of sin theta, that will give you minus cos theta. So on applying the limits, automatically because of that minus sign, theta dash will come first, and cos theta, that will go as a second term. So it is Pe cos theta dash minus cos theta. So this is your work done. Okay, so now we know that work done is equal to potential energy difference between the angular positions theta and theta dash. So it is rewritten as u of theta minus u of theta dash is del u, and that is equal to the previous equation. We are writing it once again, minus, expand this, Pe cos theta dash minus Pe cos theta. So they have written the second term first and first term second. So minus Pe cos theta plus Pe cos theta dash. Suppose we are moving it from theta dash to theta already, as we know. Suppose if theta dash is 90 degree, if it was 90 degree, if it was perpendicular to the field, and if you are rotating it through some angle, we can take theta dash to be 90 degree itself. So cos 90 is 0, the second term becomes 0, and Pe is that is u is equal to s minus Pe cos theta. See, please look into that. You are using small letter p for representing the dipole moment always. Okay, so it is u is equal to, capital U is equal to minus Pe cos theta, that is expressed in dot product as minus P vector dot E vector. Okay children, so what happens when this theta is equal to pi? Substitute in this formula in 1.51. When theta is equal to pi, you know that it is cos pi is minus 1, so u is equal to minus Pe. So the value is maximum, cos pi is minus 1, so it is minus into minus becomes plus, so u is equal to Pe, so it is maximum value. If theta is equal to 0 degree, Pe is minimum, that is potential energy is minimum. So when cos 0, when you take the value to be cos 0, what happens? U becomes minus Pe, and that is the minimum value. So this potential energy varies between minus Pe and plus Pe as we get studied so far. Okay, so why the potential energy is maximum when theta is equal to 180 degree? Can you guess? So look at the diagram, have a close look at the diagram. When you are placing it as theta is equal to 180 degree, how we are placing it is, the plus q charge will come to the left and the minus q charge will come to the right side. Okay, look into the direction of the electric field, it moves towards the right. So that means that there must be a positive charge in the left side or negative charge in the right side. So we are trying to align the dipole in the direction opposite to that of the field, and that is why we have to do more work, and that is why the work done is, that is potential energy is maximum here. Opposite of it happens in the case when theta is equal to 0 degree. Okay children, so let us finish it off with a simple example problem. A water molecule has an electric dipole moment of 6.3 into 10 power minus 30 coulomb meter. So small p is given over here. Yes, sample contains 10 power 22 water molecules with all the dipole moments aligned parallel to the external electric field of magnitude 3 into 10 power 5 Newton per coulomb. So the magnitude of electric moment, that is dipole moment, and electric field is given. So how much of work has to be done to rotate the water molecules from theta is equal to 0 to theta is equal to 90 degree. So let us consider one water molecule for now. In that case, the work done is given by the formula del U is equal to U of 90 degree minus U of 0 degree, because we have to move from 0 to 90 degree. So U of 90 degree is 0, you know it already. So it is, the remaining thing is U is equal to minus PE cos theta, because minus PE cos 90 plus PE cos 0 degree anyway, but cos 90 is 0 already. So it is simply going to be PE now. Okay, what is P and what is E? It is given in the question. Just to multiply them both, you will get the final work done. So this is just for one water molecule. So what will be the total number of water molecules given in this case? It is 10 power 22. So multiply this 10 power 22 with the work done to find out the total work done to align all the dipoles parallel to the electric field. Okay children, so today we have discussed about very interesting topics: equipotential surface, then we have studied about electrostatic potential energy of collection of point charges. We have discussed about the relation connecting electric field and electric potential, and finally we had concluded with the potential energy because of the dipole placed in a uniform electric field. Okay, so I want to conclude today's session with Carl Sagan's favorite quote of mine: the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. To know itself. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. That is, you are studying about yourself. That is what you are studying. When you are studying about universe, that means that you are studying about yourself. That is nothing but you yourself is the universe. That is what he tries to convey. So this is similar to what we have discussed in the first class. I think you may remember. Andathil ulladai pindathilum undu, pindathil ulladai andathilum undu. Okay. Actually, we have one more quote of Carl Sagan which explains exactly the same meaning. Please Google it and find it out what is that quote. Okay. And remember, you don't stand for you stand for universe, and you are the universe. Thank you children.